This is 8.107. It's on page 476. The coefficient of static friction between block B and the horizontal surface and between the rope and support C is 40%. Knowing that the mass is 12 kilograms, determine the smallest mass of block B for which equilibrium is maintained. Let me sketch this. This is a pretty straightforward one. Shouldn't take us very long. So mass of B is unknown. This is block B, of course. And we'll just break that there. This is ground. There's a rope wrapping around the feature C here on the end with a mass, which is, what did they say, 12 kilograms? The coefficient of friction between the block and the surface there is 40%, as well as under the round feature. So first things first, we're going to notice that there is a difference in tension between the rope on either side. And of course the wrap angle beta is 90 degrees. Okay? So basically, let me ask you, which is going to have the higher tension in it? This rope or this rope? Notice if we had a pulley here, they'd have the same tension, right? But it's not. It's a feature that's just static.
From A to C.
From where? From A to C?
Yes.
Yeah, so you think this is going to have, I agree, because think about it, we're on the verge of slipping this way. What does that mean? If I were to draw feature C, which way is friction acting on the rope? Well, if we're on the verge of slipping, then motion is this way. We're taking C as our reference. Motion is about like this, therefore friction must be up like this. If friction's up like that, that means there's less tension because the friction's helping to support, you see? So, if we know how much weight is represented by A, well that's mass times acceleration of gravity, 12 kilograms times 9.81 meters per second squared. Calculate that for me if you would. That's what, roughly 120 or so newtons, a little less.
I have a question.
Sure.
Why did you put, is that B equals 90 degrees or
That's
like
beta. That's an angle beta equals 90 degrees.
Why did you put?
Because that's the wrap angle, if you look at the problem. Can you see the problem?
Yeah, it's just not.
Well, notice that there's a tangent point at the top and a tangent point on the left, right? Basically, the rope loses contact here and here.
Yeah.
You see, so that's why I chose those 2 points. Wherever we lose contact, there must not be any friction, right? So that's why I chose those. Good question. Anybody have a number for the weight of A?
117.72.
Thank you. 117.72. Thank you. All right, so could we calculate the tension on the other side?
117.
Oh, thank you.
Yeah.
I wrote 177. All right, could we calculate the tension on the other side? Sure, we just need our handy-dandy equation for this, right? Which is the whole point of this entire section. How did that equation go? It said T2 over T1 equals E to the mu S beta. All right, where mu S is the static coefficient of friction and beta is the wrap angle. So why don't we calculate this? Because I want you to make one more note on the equation in the textbook so you remember it. Let's calculate what E to mu S beta is. Mu is 40%. Beta is 90 degrees, except wait a second, we've got a problem here. Guess what? The angle beta always has to be written in terms of radians. You need to make that note on the equation. Go to page 472, make a note on equation 814 that beta had better have units of radians. In other words, how do I convert 90 degrees to radians? Do you know?
Like pi.
Over 180.
Yeah.
Okay. Or I could just remember that a 90-degree angle is a pi over 2 angle. That would work as well. Okay. So basically we need pi over 2 times 0.4. There's one more note to make, but go ahead and tell me this number. You know where E is on your calculator, right? I hope. If you don't find it. So you need to take e to the power of 40% of pi over 2. What do you get when you do that? Probably got to get 1 point something.
1.87.
Anyone second that?
I second it.
So what does that mean? That means the tension on side 2 is more than the tension on side 1. So I want you to make a note. Side 2 is the tight side, side 1 is the slacker side. It's less tension, okay? Or you might write it this way, T2 greater than T1. In other words, this side is T1, this side is T2. Okay, go ahead.
If we had if we had a decimal below 1, would that mean that T?
You will not
was
get,
greater?
you will not get a decimal below 1. E is 2 point some odd. So. Two point seven something, I think. So now we can calculate T1 because we know T2, don't we? All we have to do is take 117.72 and divide it by 1.87. In other words, T1 equals T2 over E mu S beta equals 117.72 over 1.87, and these are newtons. So tell me what the tension is on the slack side, the so-called slack side.
It's 62.95.
62.95.
Yes, sir. Good here.
Thank you. So now all we need is a free body diagram of block B with the normal force, weight, friction. Does friction act to the right or to the left on the block? Well, the block's about to slide to the left, isn't it? So if we're standing on a reference that is not the body of interest, the body it's sliding on, the block is about to slide to the left, therefore friction's opposite to the right. And then there's also the tension, T1, acting on the block. Okay? And that's it. Now the weight is just mg. How much will the normal force be? Well, the body's not accelerating vertically, is it? So that wouldn't this just be equal to mg? That's not always the case. Be careful about this. That doesn't always happen, but in this case it is. The weight and the normal force must be equal to each other because this block is not accelerating vertically. All right. The friction force should be at its maximum, so it would equal mu n, but the normal force is just the weight, so mu mg is equal to the friction force. Okay? In order to have static equilibrium in the horizontal direction, taking a typical xy coordinate system, the tension and friction must sum to 0. Those are the only two forces acting in the horizontal direction. Okay? So that means the friction must be equal to the tension. And what was the question? The question was, how much does the block have to weigh so it doesn't move? Right? I found the smallest mass of block B. Okay. Well, that means that the friction, which is mu mg, must be the tension that we've already calculated. Where is it? I thought I wrote it down there. It's 62.95 newtons. So if we rearrange this, take T1 divided by mu g, that would be the mass required. So that tension is 62.95 newtons divided by the friction coefficient of 40%, divided by 9.81 meters per second squared. Put an X in there to indicate multiplication if you'd like. What units will we end up with?
Newton meters.
No, that newton meters are a torque. We need to end up with mass. And besides, where did the second squared go? You could say it's newtons times second squared over meters,
Yeah.
but what is that really? Well, what's a newton?
Kilograms meters per second squared.
Kilogram meter per second squared. See what happened? The meters per second squared went away and we've just got kilograms. Okay? So, 62.95 divided by 0.4, then divided by 9.81 equals what? By the way, on your calculator, you don't have to type 62.95 divided by open parenthesis 0.4 times 9.81 close parenthesis. You can simply say 62.95 divided by 0.4, hit divided by again, 9.81, and it'll all be the same thing. Because all the divided by symbol does in your calculator is say what comes after this goes in the denominator. Works that way in Excel as well. Anyway, what number do we have? About 12, 13, something like that?
I have 16.
16, seems reasonable. So 16 even, or
No, 16.04 or something.
04?
Yeah.
There's how much mass we have to have for block B to not slide. Okay? If block B doesn't have that much mass, then the normal force will be less, the friction force will be less, and the tension from this mass will overcome, and the block will slide. Any questions? All right.